Hi guys, welcome to tutorial 2, question 2. Let's do this. Like my other videos, I'm going to put the question right here. Read it over, attempt it yourself, and then we'll go through it together. But we got to start with our base case. Well, what is the smallest full binary tree out there? Well, it's the tree with a height of 1, of course, and that is a single lonely node. A single lonely node has odd number of nodes because it's just 1. So that's our base case. It checks out, it works out. 1 is odd, and that's it. The next step will be to do our inductive case. Now, like always, as you know, we got to make our assumption. So our assumption in this case is going to be, suppose that any binary tree of height, 1, 2, blah, 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 until h has odd number of nodes. So then next step would be to prove that this works out for h plus 1, that h plus 1 tree also has odd number of nodes. So now we gotta do the h plus 1 case. But for 1 second, let's just put that to the side. I just want to make sure you guys understand what's going on. Let's say we have a tree, like we have tree with a full binary tree, and it has sub nodes and has children and everything, right? The question is, let's not think about it as a tree. Let's think about it as a root with just 2 children. Now, granted, those children have children of their own, but let's just say, this node has a child on the left, a child full binary tree on the left, and a child that's another full binary tree on the right. Let's just think about it like that. Now, the question becomes, well, if it's a full binary tree on the left child, that means that one has to have odd numbers, so that's odd. If the right child is also odd, well, okay, odd plus odd is, even, because those lonely ones become doubled, so it's even. And then there is the root directory itself, so it's, even plus 1, and that's odd again. So our full binary tree that we said, let's imagine, is odd. Now, I'm going to tweak it a little bit so it works for our case. Let's assume that those children on the left and right had a height of h, and because, they're connected to a root that, that full binary tree has a, height of h, now the entirety of that is going to be h plus 1. And we just talked about it. We just talked about how if the left child has a height of h, and right child has a height of h, and this is odd, and this is odd, even, plus the root is going to be, and again, odd. We just proved that our h plus 1th case is also going to be odd, and therefore, we just proved this question. Well, that was the proof with complete induction. Now, the question also asked for structural induction. I'm going to go through it quickly. It's very similar. And when it comes to structural induction, we know that we have the recursive definition for T being, set of full binary trees, and it's defined as the set of non-empty binary trees, just like what I just said. And any single node, a single node, like our base case in the complete induction, is in T, of course, because it matches that definition. And if T1 and T2, some T1 and some T2 are in T, right, are, set of full binary trees, then a new tree with a root of R at the top, and then T1 on the left and T1 on the right are also going to be in T. This question is very similar to the example in the readings for the notes.pdf that's on the website, on page 19, if you give that a check. And that's it. That's the structural induction, and very similar to complete induction. I personally like the complete induction one better, but preferences are preferences. All right, guys, I'll see you guys in the next video. That's all for this video, and yeah, see you there.